So in our elimination reaction, which I'm now summarizing as E1, but we're looking at our elimination reaction, and in this case the 1, just like for our SN1, meant unimolecular. What we want to be able to address is our full-on mechanism behind this. So in our 1-type mechanism, geez, I have none of the summary stuff on here I wanted. In our 1-type, we said that we break the leaving group bond, then we break our carbon-hydrogen bond. Okay, so there's our carbon-hydrogen bond drawn on, and so what we're talking about is breaking those two bonds. If we break those two bonds correctly, we should have enough electrons to go through and make a pi bond that we see in the far right. Okay, so again, just like with the substitutions, we've got our basic kind of pieces behind this. Here's our substrate. Our substrate includes all of that material. Officially, yes, there's another hydrogen there. The leaving group, as we addressed before, there's our leaving group. And notice here our red, instead of it being a nucleophile, we're specifying it as a base. In the E1, it's a little bit more complex. It's not so much base as in not nucleophile. Why not nucleophile? Well, if there was a nucleophile, what do you think would happen? An SN, N for nucleophile, substitution reaction. So we're looking at a situation where there isn't a nucleophile. The solvent could play a role in this, and then we'll introduce these terms of regiochemistry, which I'll address in a second, and kind of benefits, which are slightly different than how we looked at the substitution reaction. Okay, so before we start digging into those too much, let's go through and take a look at our mechanism. So we'll erase all of that fun stuff and address our mechanism. So for the mechanism, we needed to break the leaving group first. Okay, so the leaving group is supposed to leave with the electrons. So let's do it. The electrons move to the leaving group, and what do we form? Okay, well, what we're going to form is a carbocation. At this stage, we do have the potential for rearrangements, so we should consider it. But this particular structure we don't have to worry about because there is no rearrangement possible, okay, which is kind of nice. So now what can happen? Well, in the case of substitution, we would now have a nucleophile come in and share electrons. But what we just said about the elimination reaction is there's no nucleophile. So I have to find somewhere to get electrons to stabilize that carbocation. Okay? If we can't find them outside, if we can't find our sources from outside, we have to go inside. So we're going to have to go within the molecule. There are tons of bonds within that molecule that have electrons. For instance, I could take the electrons in this bond and I could put them on that carbon. What would the result be? For those of you drawing, stop and actually look at what we're doing. Okay? We're adding those extra electrons there. We have this extra carbon floating around, so it might be helpful to draw it as a CH3. What happened to that CH3? Well, it lost electrons, so it is now positive. Before we even look at the larger part of this structure, we started with a secondary carbocation, and now we're ending with a zeroary carbocation, or a methyl carbocation. That was a horrible mechanistic step. Okay, so sourcing electrons from that bond is a bad idea. Okay, so let's look at the other piece. What about that carbon? Well, if we go through and address it, those are the only things connected to it. So if we go through and evaluate it, it is technically neutral, okay? But the electrons, that lone pair, the whole point of that was to stabilize the positive charge, right? It's technically not stabilizing the positive charge. To stabilize the positive charge, you would have to place electrons into the orbital that was causing the positive charge, which would be a p orbital. The electrons in the bond that we just broke are perpendicular to the p orbital, okay? Which nobody likes that description, but that's what's going on, which means nothing about what we just attempted did anything to stabilize the carbocation. And if anything, it made things worse. Okay, so what we need to look for in the elimination is a source of electrons that actually stabilizes. There are a lot of different places that you could pull electrons from. Okay? What I would recommend you do is you pull electrons from every single one of those. So we've got 4 things on there. Blue, green, which I then hid with another blue, green, purple, and red. You should draw those out and see what they result in. Okay? Why? Because you need to be able to acknowledge what is wrong. You have to look at that. So you need to draw that out so that you can see it and think about it and acknowledge that it's wrong so that you don't make those mistakes. Okay? What we're going to show right now is the right step. The right step is that we're going to take electrons away from that red hydrogen. Okay? This is not a rearrangement. Okay? Because in a rearrangement, we're moving the electrons from the atom of hydrogen, technically that bond, and we're moving them to the carbon of the carbocation, that purple. If you notice where that arrow is stopping at the bond, not at the purple atom, which means what I am doing is showing the electrons exist in a bond. That means 2 more electrons are in that bond. I now have a pi bond or a double bond, and there's the formation of that product. One of the things that tends to trip students up, though, is now what picked up that hydrogen. Okay? Because if we look at this, I now have just H plus chilling out there. You go, oh my God, H plus, that's a horrible thing. We can't do that. Yeah, yes and no is really the unfortunate answer with that. So how are we getting that bond to break? Well, in the E1, we are very commonly adding heat to the reaction. That heat will cause that bond to vibrate enough that it weakens and it can break to form the alkene. Okay? Other things that we can do is we can reference perhaps the leaving group. The leaving group left with electrons, it could have potentially shared with that H plus to stabilize it. We're probably running the reaction in some kind of solvent. That solvent could have electrons that could potentially stabilize that hydrogen. In the E1, don't stress about the hydrogen. Okay? Which is not a really nice thing to say because in the E2 we do have to stress about it. Okay? But in the E1, you just remove it. It just disappears, just falls off. It's the way it is. Okay? So, we then had those primary categories that we could evaluate. So now that we have our mechanism, we could go back and think about all of our pieces. Okay? So in our substrate, well, what kind of substrate do we want? But before we get into that, we should really be considering our rate, because the rate is going to determine where our reaction goes. Well, our rate is going to be dependent on the rate constant times the concentrations of the reactants in the rate limiting step. Okay? Well, where's our rate limiting step? We start neutral to become charged to become neutral. If we were thinking about an energy diagram, we've got neutral, charged is higher, and then neutral. Which of those is likely to have the highest activation energy? Probably the first step. Okay, this is where our energy diagram can help us out. So that first step is our rate determining step. How many reagents are involved in that first step? Well, it was just the substrate. Okay? So we're really only concerned about that substrate. Well, if I'm considering the substrate now, primary, secondary, tertiary, I need to form a stable carbocation. So the leaving group must leave. So again, I need that good leaving group, so we could add that in there. Good and useful information. But then I also have to be able to form that carbocation. Well, that carbocation needs to be stable. What would make it more stable? How about if I got rid of a carbon? Oop, no, that would make it primary. That would actually make it worse. So I don't want primary. What if I added another carbon? Oh, well, now it would be better. Okay, so if I'm looking at substrate stabilities, I want a tertiary to be more stable than a secondary. Why? Because what I'm looking at is a carbocation. So if I consider the carbocation in my mechanism for an SN1, it helps to drive the presence of that substrate. Okay, so that's kind of useful and neat. Okay, this also is kind of a direct result of our activation barrier. If I'm trying to speed this reaction along, that transition state, that peak, is going to be closest in energy to the intermediate. That was our Hammond postulate. If I can make that intermediate lower in energy, what happens to my activation barrier? It gets shorter. Okay, it gets a little bit smaller. So I want to stabilize that carbocation as much as possible. Tertiary substrates are great. Secondary substrates are great for that as well. Okay. As far as the base strength is ultimately kind of irrelevant. Okay. Similar to our SN1 where we said the nucleophile was irrelevant. Okay. Why is it irrelevant? That base would be coming in a fast step of the mechanism. I don't really care. Okay. The next part is the solvent, because we talked about that before in the past. We might, well, why don't we talk about that now? The solvent, I'm really just going to say, it's not that it's irrelevant, it's that it's misleading. Because when we go through and look at the elimination reactions, both E1 and E2 tend to have the same type of solvent, and they're artifacts of the presence of the base. Okay? And so because of that, I would just say, when it comes to using the solvent to differentiate elimination, don't, because it's too misleading. Okay? So, stereochemistry, cool, out the door, totally don't have to worry about it at all because we don't have a stereo center in our product. Or sort of do we? When we look at our product, we could have formed the product where we had the cis result versus the trans. Both were potentially possible. As long as that hydrogen was there, it could eliminate or it could be removed to dump electrons into that parallel carbocation, okay, that empty p orbital. So both of those are possibilities. This isn't officially regiochemistry, I think. Actually, I'm going to change my mind and say this is regiochemistry. Deciding whether we get cis or trans. Both are possible. Which one would we expect to be in the larger percentage? Okay? Or are they equal? Well, the trans is more stable than the cis, so the trans should be favored over the cis. Why is the trans more stable? Trans is more stable because we have these larger electron groups on opposite sides of the pi bond versus on the same side of the pi bond. So when we're running an E1, we would expect the trans product to be our predominant product. Okay? That doesn't mean the cis can't form. It just means it's going to form to a lesser extent. Okay? Benefits, I wouldn't really push in benefits as in more complications. If we take a look at this rate law looks really familiar. In fact, it is the rate law for an SN1 reaction. So if I'm going to try and run a mechanism and I'm going to try and do an elimination, the E1 could be a challenging elimination to run because it could result in an SN1 product also. So that would decrease yield. How could I limit that? I could make sure that my base or whatever species is there to help remove that hydrogen is not nucleophilic. Because if it is nucleophilic, I now increase the odds of running the substitution. So I want to limit that as much as possible. It's something that I need to be considering when I'm looking at that E1. Okay. So with that, we'll stepwise through and make it all look nice and pretty because I've got some of those summaries on there. The substrate, we want a stable carbocation. The leaving group, we said already, should be good. Base, we don't want one. Heat is typically the thing that's going to help us push through with our eliminations. Solvent tends to be polar protic. I'd be very, 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 very careful putting too much weight in that aspect. Regiochemistry, we primarily favor the trans product. We didn't address this concept of Zaitsev. We'll see that later on. Okay? And then where we have benefits are really complications. These aren't benefits. These are actually bad things. We formed a carbocation, so rearrangements are possible. And the big one, it directly competes with an SN1 mechanism. So we have to be aware of that and watch out for that when we're looking at the reaction. Because I don't think I have a slide that looks at an energy diagram for the E1. Let's go ahead and really quickly draw this up. We've got our reactant. We've got our intermediate carbocation with a nice full step. But then I want to address this concept of our product. Where should the product be? Okay. Should it be lower in energy than our reactant? Should it be higher in energy than our carbocation? Well, the carbocation, hopefully you see that doesn't make sense. Okay, so we get two possible locations for the product. Okay, and that was an attempt to show it higher than our reactant but lower than our carbocation. So, two options, A and B. If you said B, you might have said B because if it's going to work as a reaction, we would presume it would be exothermic. The problem with that is that if I compare the starting material to my product, what is the difference? Well, they're both neutral, except the product has a pi bond. And pi bonds are made of p orbitals, and p orbitals, I know from my atomic theory back in Unit 1, are higher in energy than the hybrid s orbitals in my sp3 sigma bonded structure, which means A is actually the appropriate answer. Our product is actually higher in energy than our reactant. In the formation of our elimination products, these are endothermic reactions. We have to put heat into these to get these to really go, and we run into all sorts of issues with reversibility behind them. So we do have to be a little bit more careful synthetically when we go through and do an elimination reaction. All I want you to be aware is that that product is actually higher in energy than our reactant. Okay, so with that, we'll end the elimination or E1 elimination, and we'll start the E2 in just a second.